Okay, let's begin. So I've posted more of the videos on the weekend so that you should have everything up to today, at least on YouTube if you want to have a look, review over that. May help when you're studying, may not. Okay, today I want to talk about, again, we're looking at two-dimensional data and think about how we might transform that data and how we have in fact already used some transformations. So one thing that we used a few times is looking at changing the aspect ratio, and that allowed us to see different patterns. Largely those patterns that were near a 45-degree angle seemed to stand out, so we could see trends or the cyclical behavior. And that's really just a changing in the relative size of the scales of the data. So it's a rescaling in the visual in what's being displayed of the data. Okay, so that's what aspect ratio is changing the relative scales of the data as they appear on the screen. Other thing we did was taking a square root. I just did this very quickly in passing, saying it might be a good idea to take a square root of those sunspot numbers. That these things, I may have said these look a little asymmetric, and when I take the square root, they got spread out a little more, and so that with these the cycles are a little easier to see being spread out. Okay, so it reduces the peaks and deepens the valleys here in the cycle. So those are two transformations that we've looked at. One simple relative scaling, and the other an actual nonlinear transformation, taking the square root of these counts. You see the effect if I look at the density of the sunspot counts. So I've got a density estimate of the sunspot counts on the left. And if I take the square root of the count instead of the count itself and get a density estimate again, I get the density as appears on the right. And you can see that density on the right is far more symmetric. Right? This one is very skewed out to the right here with a long right tail. And now we've got a much more symmetric looking distribution. And that's what affected that change that we saw in the deepening the valley, sort of sorting out the valleys and summits of the peaks of those cycles in the sunspot data. So this nonlinear transformation is doing something funny. It's actually changing the distribution of the data. Okay, it's not just moving it around like a location change would be, or just changing stretching the axis or shrinking the axis like a scale change might be. It's actually changing the density. So that's an important thing. Another transformation that we've used in the past already is something you maybe didn't realize was a transformation, and that was just getting the ranks. So if I take, so here's the sunspot data again, the raw counts, the square root of the counts, and now instead of the counts themselves, I'm just going to rank all of the counts. So the smallest count gets rank 1, the second smallest gets rank 2, etc., and the largest count gets whatever the largest, how many different measurements we have here, okay? And you see that still preserves that cyclical behavior, and it perhaps makes it a little easier to even detect. Okay? So that's another transformation, and one that is quite strange. In fact, a nonlinear transformation that has a particular effect. One thing that you know that it does is it takes all of those counts which had some density, some distribution, and changes it to a bunch of numbers from 1 to n. If I was thinking of the distribution of that collection of numbers 1 to n, where every number appears, what does that distribution called? Yeah, it's just a uniform. So I've changed it. These guys now have a uniform distribution, but I'm still preserving that structure that I see in that time series. Okay, so it's another nonlinear transformation. So here's what we've looked at. We looked at some scale transformations. They're linear. They preserve the order of the data, so that if x was smaller than y, when I rescaled it, x was still smaller than y, provided I had a positive scaling. Square root. This is a nonlinear transformation, also order preserving. Of course, it has to work on non-negative numbers. We can't have negative numbers under the square root sign or we end up with complex values. And the ranks, they preserve the position here. It's only preserving the order of the data. It's definitely nonlinear, preserves the order. Okay. And you can see how that works. So there's some numbers, and there are their ranks. So that the smallest number here is in position 4, right there from the end. That's the smallest number, first rank. Okay? So those should be all pretty familiar. But I appreciate that everything we've been doing has been a transformation of the data. We just haven't really called it that. So what I want to look at is a family of transformations that have some pretty attractive properties that we'll see in a minute. And that is a power family. So I want to think about transforming the data x for x, assume that it's non-negative, in fact assume it's greater than 0, and apply a transformation to that raises the x to some power alpha, rescales it, and translates it, relocates it. Okay? So there's a nonlinear, and then a scale and location change. So that's the family. And that'll index that by alpha. That's for alpha not equal to 0. For the case alpha equals 0, I'll take the logarithm instead of the power. Okay. So for these to preserve the order, so that by the transformation it hasn't changed the order, I'm going to require certain constraints on the various parameters. So when alpha is greater than 0, I want a to be greater than 0 and a to be less than 0 when alpha is less than 0. So for example, if alpha was minus 1, and if I do 1 over x, big numbers just became very small numbers. Small numbers became the big numbers, so I've swapped the order. So by changing the sign of that a, I've just switched the order back again to the original order. So that's what these constraints are all about. Another way of writing this with fewer parameters here, but just for mathematical convenience, is to think about this just as a function of this power, and that's why we call it a power family. This is principally just for mathematical convenience rather than this messy expression up here. This is probably what we end up programming a little more carefully, but this is where we do some mathematics. And why is that? Well, if I take alpha can be any number now. If alpha is positive, things are going to work out in that I'll have a positive scale. If alpha is negative, I'll get a negative scale because I'll just use minus alpha. Sorry, alpha here will be negative, so that'll be minus something times x, so that'll to preserve the order. And when alpha equals 0, well, when alpha equals 0, we've got 1 minus 1 divided by 0, which is not so good, but we know how to do limits. You recall from first year calculus. So you can find the limit of that, and the limit of that as alpha goes to 0 is just taking the logarithm. So now we've got a smooth transitions for negative alphas to positive alphas right through 0, and it's nice and smooth. Okay, so that's a mathematically convenient form. Any questions? Okay, so let's see what happens. I'm going to apply this transformation to data that you know well already. So this is systolic blood pressure for all of the patients in the South African heart disease data set. And the histogram is there with the density overlaid, density estimate overlaid. And you can see that that density estimate is skewed. Right, it's got a long right tail. And if I were to look at it in a Gaussian QQ plot, with a self-calibrated QQ plot, you can see that that definitely does not look normal. These values are way outside of the envelope, and you see that curvature is typical of a skewed distribution with a short left and long right tail. Right, so you should be, by now, be able to look at this and imagine that's what this will look like, or look at this and imagine that the density will look like that. Okay? So we're going to look at what happens if I change alpha. So to do this, I'm going to look at, introduce a power function. I'm just going to use that simple mathematical one, mainly because it just fits on one line of code here in my slide. It's not exactly the most numerically stable way to program this up, but it'll do for our purposes. And look at the results for a number of different values of alpha, from -2, -1, -half, -1/3, 0, and then the positive versions of the same. Okay? And the code will do this. I'm just going to plot the histogram and overlay the density estimate and look at the QQ plot beside it. So let's look at these one at a time in descending order of alpha. So the highest value of alpha. Alpha equals 2. So when alpha equals 2, the histogram and density of the square of the systolic blood pressure still looks very, very skewed. And you see that it's appearing in the normal QQ plot. So if anything, this tail is really far out there by the size of these quantiles. Very skewed distribution, short left tail, long right tail. Let's reduce alpha. Alpha equals 1, that's our original data. Not quite as skewed. So in fact, when I squared it, I made the skewness worse. Okay, that's more skewed than the original data. If I take this square root, I think is next. This tail is starting to come in, getting closer to the envelopes. It's starting to look a little more like a Gaussian. This tail's not quite as stretched out as it was before. This beginning to look a little more symmetric. 1/3, a little more symmetric again. The logarithm, more symmetric. Still a long right tail here, and you're seeing that outside the envelope. That does not look Gaussian. -1/3, still outside of the envelope. -1/2. -1. Now I'm starting to get something that looks plausibly like a Gaussian. Okay, so 1 over the systolic blood pressure actually looks like it could be have come from a Gaussian distribution. If I keep going, 1 over the square also still looks like it comes from a Gaussian distribution. So we can do these transformations and actually get this thing, because we're changing the distribution of the data to look more and more symmetric, or less and less symmetric, depending on how we choose our power. Make sense? Okay, so here's what's happened. If I'm looking at the systolic blood pressure, the original data is sitting here at alpha's 1. That's the original data. When I increased the power, I got even more asymmetric, more skewed data. When I decreased it, it's moving along, becoming more and more symmetric, arguably fairly symmetric here at -1, -2, and -3 actually goes a little farther, starting to get a longer left tail now. Okay, so you see how changing this power is actually changing where this mode is and what the shape of the tails are. So if you look at this mode is to the far left of the density, a little moving a little closer to the middle, a little closer to the middle. Think about that moving. That mode is actually moving from left to right as I change that power. It's an important observation. Any questions? And if we look at the QQ plot, you'll see the same thing, the straightening out here. The data is here, and if we choose a higher power, we've made the situation worse. It's more asymmetric, more skewed, and we lower the power until now we're fitting in. It looks like it could be Gaussian here. And we keep going, it's starting to peel off in the other direction. The tails are going off in the other way. Okay, so you can go too far. So there should be some kind of ideal choice for what that alpha should be. So let's get a better sense of what's actually happening here. And to do that, I'm going to look at Loon. And so we're going to have some interactive graphics here. I'm going to write a function power. This is going to do all of the work. It's going to take some data and some other information about labeling, etc. And I'm going to go get the normal quantiles for that. I'm going to get a plot of the Gaussian quantiles. I'm going to see the Gaussian quantiles themselves. And then I'm going to get a histogram. And there's a funny thing in here. What I've done is I'm using a command that you haven't seen yet, I don't think, that I'm going to get a top level window because I'm going to start producing a new graphic. So this top level window, this top window here that I get from TK, top level, and when I make my histogram now, I'm going to say its parent is that window. So that's the essential feature there, that I've got that window. Now I can stick that in when I create the histogram. I'm going to have an alpha level, alpha level, which is going to be some variable, TCL var with value 1. And then there's going to be a funny thing here called a scale, and that's going to be a slider. So I'm going to have a slider here that's going to be a horizontal slider. It's going to call it power X. It's going to go from lowest to highest and with these steps, that resolution. And the variable that it's going to track is the variable alpha X. And then these commands are about building that thing. I'm going to put the slider on the bottom, and then the histogram will go in above that. And now I'm going to have an update function. So this update function is going to take arbitrary arguments. I'm not specifying what they are. They're going to be able to read the value of that alpha, get some new power of the data, applying that power function that we wrote was just the x to the alpha minus 1 over alpha, and then update the plot with this configure command, updating the plot with the new x value for the vertical axis, and updating the histogram as well with the new data. And I'm making sure the histogram scale to the world. So the last thing I'm going to do then is I'm going to configure that slider so that whenever it changes its state, it will call this function update, this function that we just wrote here. All right, so that's a quick tour of how you can build things pretty arbitrarily. So let's try that. So I'm going to right, so there's our histogram with the slider at the bottom. There's our plot of the quantiles. Move this down out of the way. And on the quantiles, we'll just put some background guide on that. Histogram we've seen before, so that we can change this thing. You see it's skewed on the right, so it's got a long right tail. And the mode is over here on the left. This slider here is the power that we have, so power is 1 right now. If I click on one side of it, it'll change the power. I'll go up. So if I click there, it'll go up 1 step there. And you see the quantile plot changing as I increase the power, and this density is becoming more and more skewed. If I go the other direction, let me just grab the slider and start moving this. You'll see that this histogram is becoming more and more symmetric, and that quantile plot's looking straighter and straighter. So there's that -1 that we looked at before. So you can interactively explore this and say, I've got a Gaussian quantile plot on the right hand, and I can just explore these powers. So by the time I get to -4.4, I've actually got a skewed distribution in the other direction. The mode's over here on the right, the tail's stretched out to the left. You can see it's piled up here on the right and stretched out on the left. Okay, any questions? All right, so you can just play with this at your leisure and see how you might choose a power that seems to work and what range enough that it looks like it could have been generated by a Gaussian distribution. So one way to remember this, how you might make changes, is to think about what we saw in the picture a minute ago. And I'll just tell you, look at this again. Think about where this mode is. Where is that bump? And where's the slider? The bump's on the right, the slider's on the left. When I move over here, the slider's on the right, the bump's on the left. The mode's on the left. So principally it's telling me that if this mode is on the left, I want to move the slider to the left. If the mode's on the right, I want to move the slider to the right. So you got a little simple way of remembering which way should you go with this slider. So John Tukey suggested that you think of this as if we've got a ladder of transformations. So we've got all these powers arranged in a ladder where the lowest values are at the bottom rungs of the ladder and the higher values are at the higher rungs of the ladder. So the raw data begins at 1 and you can move up and down this ladder. So sometimes called as Tukey's ladder of power transformations. And the suggestion is that if you see the bump on the low side on the left, then you need to move down the ladder. If you see it on the right, on the high side of the X, you need to move up the ladder. So just by, if I gave you a plot of this, say for example on a midterm examination, I told you that was actually the square root of the sunspot data or something else. And I say which of the following transformations might make that look more symmetric, you know that you need to move up on, you need to make this go up, you need to move up on the ladder here. Okay? So if it's concentrated on higher values, you need to move the power up. If it's concentrated on lower values, you need to move the power down. So it's very simple mnemonic, called the bump rule. So just look at this again for a couple of other examples. One where we know the distribution itself, a chi-squared. Hopefully get the right chunk here. Right, so here's a chi-squared with 200 observations. Let's just get rid of these old guys. And the Gaussian QQ plot. You can see the values. And so the bump is on the left, on the low side, so I should move lower on the ladder. Bump is still on the left, move lower. And eventually, it looks about right. If it goes over here, the bump's on the right. On the high values, I should move higher on the ladder. So that's going to be able to straighten this out, and you can see that I can change the skewness of that chi-squared very simply. And a range of values for which that Q plot looks like it could be Gaussian. Might look better if I make these bins wider. Okay. Another example. Well, here's the duration of the old faithful geyser, and you recall that one of the dominant features here was that bimodality, and you can see that in the quantile plot. Quantile plot or in the histogram itself. And again, let's just make these a little bit wider. So our rule is not very helpful now because I got two modes here. So I can't say where should I go up or down. Let's see what happens if I go up. If I fix this, I'd like this to be a straight line. So let's see if we move this up. That's doesn't seem to be working so well. Let's try the other direction. Also not working so well. I mean, that looks like it's getting straighter, but what's really happening is you've got this point down here, don't forget. So it doesn't look like we're going to be able to do much about this. So these transformations, these power transformations, are just going to be working well for unimodal data. Right? So you've got that one mode that you can move around, try to make things a little more symmetric. Not going to work for bimodal data like we see here. Any questions? Yes?
Why do we want to apply a power transformation that makes things look more symmetric?
Good question. The question is, why do we want to apply a power transformation to make it look more symmetric? Why do we care that it's more symmetric? So there are a bunch of reasons. Let me give you the most trivial reason is when things are all piled up. With asymmetry often means that things are really piled up in one area, and you've lost detail in that area. So just power transfer, you're going to spread those out so you can see the details where it's really dense. That's one reason. On a mathematical thing, sometimes you've got some theory that works pretty well for Gaussian distributions, right? So if I could transform the data so that now this looks like a Gaussian distribution, then it could have been generated by a Gaussian distribution, then my theory should apply, roughly speaking, at least to that situation. For my money, the former is the more interesting reason, is just to spread out that dense stuff. You might also notice that if I have a bimodal distribution here and they were skewed distributions, these two modes in different ways, transforming these may make one of them look more symmetric and the other less symmetric. Okay? Other questions? All right. So the data must be unimodal for us to actually get the true effect of symmetrizing from the power transformations. Another reason you might have, now we're interested in two-dimensional data, so I've actually got X and Y data, so it's not just the single marginal distribution of one or the other that I'm interested in, but the relationship between them. So if I look at a plot of data, I could transform each of those coordinates, and I could transform them differently. That is, I could have a different power for the X and a different power for the Y. And I might do that to maybe straighten out the plot. If a plot shows some curvature, can I choose transformations to straighten it out? I'll show you the whole function first to begin with. We'll do this very, very quickly. So as before, I'm going to write a power function that's going to produce some visualizations. This is going to take an X and a Y. And I'm going to have two sliders, one for the X and one for the Y. So you'll see double of everything here. I'm going to have a plot. And then I'm actually going to, for the heck of it, I'm going to fit a straight line to that plot. So I'm going to fit a straight line to that plot, get the prediction. So the fit is here, get a linear model, straight line fit, get the predicted values, so I can draw the line and add that line as a layer on the plot. I'm going to have a histogram for the X and a histogram for the Y. I'm going to have an alpha for the X and an alpha for the Y, a slider for the X, a slider for the Y. I'm going to pack these into some display. And my update function now is going to be changing some labels here, getting this rescaled data for the X using its alpha, the rescaled data for the Y using its alpha level. And I'm going to actually refit the line to the new data. And then tell everybody to update itself with this configure, updating the line, updating the points, and updating the histograms with these L-configures. So one slide, so each slider is going to call the same command, the update command, this update function that we just wrote. So you look at that in more detail, but that's the idea. It's very similar to what we did a minute ago. Control, there we go. So So I just have to get the fragment that has everything in it. And this is what I executed by mistake last time. So these are mammals now. I've got 62 mammals, and I have their average brain weight and their average body weight. And I have the plot now with two sliders, one the power of X and the other the power of Y. These are the data. That's the fitted line. I can see what these guys are by including item labels. So body weight and brain weight. So imagine that it seems like as the body weight increases, the brain weight increases. There's this linear relationship that we've got here that's describing that, how that change happens. You might think, you know, if this is the representing the typical behavior, then anybody above this line, maybe that's a smart animal. Anybody below the line, that's a dumb animal. And we can hover over these, for example. Which is the smartest animal here? Anyone? Pick one. Which one is that? Left, middle, right? Middle, this guy. So that's an Asian elephant. Next smartest. One on the left. Human. So elephant's smarter than us, if we believe that. Dumbest. Maybe this guy's far on the right's farthest way. Any guess of what that might be? It's big, huge body weight. That's the African elephant. Okay. So we're looking at that kind of interpretation is a little suspect because we're saying, well, how well does that line actually fit? Everything's down here. This line is pretty much determined by a couple of points. It's not very robust, at least squares line. So we might think about transforming the data. That's the X. How should I increase, decrease the power? Bump is on the left, on the low values. On the low values, go lower. So here's the X. So I start to do that. The line's updating, right? Now suddenly the African elephant is smarter than everybody else. Humans not so smart as those two elephants. Maybe this guy's the dumb guy. But you can't, I think it's a pig, isn't it? Seems a bit unfair. They're supposedly intelligent. Still not symmetric. If I move this out down farther, make this more and more, whoop, more symmetric. I've gone too far the other way. And boy, that African elephant's the smartest thing you ever saw. Okay. So that seems to be going too far. But notice that in that transformation, I've actually introduced some curvature. This is, putting a line in that's kind of dumb. There's definitely looks like there's a curve there. Let's move this up a little bit. And you can see that curve coming into play. This says I should also, this is on the low side, so I should go lower on the ladder here, so I'll move down the ladder. That's starting, that curvature still there, but now the data are getting spread out enough that I could think that maybe that least squares line's not so bad. So let's move this down a little more. Oh, I got curve in the other direction. So I've got this curve going up to the top left, and I think if I moved it this way, I've got it pointing to the bottom right. Okay, so I've got these two sliders that I can sort of move around and just trial and error here, maybe get something that is starting to look like something I might want to fit a straight line to. Okay? And you see that they're in fact both symmetric. marginally, relatively symmetric. Again, this looks a little better if I had wider bins, so you're not focusing on the gaps. These guys look a little more symmetric. And now, that African elephant looks pretty average, as does the Asian elephant, looks pretty average. This hopefully is still us. Yep. Very, very far from the line. That one's also pretty far from the line. That's a rhesus monkey. This one's very far below the line. And that is a water opossum. Okay. So if you move these around, you have two effects happening. You're making these things more symmetric looking, but you're also straightening out this line. Straightening out a curve. So this is another rule of the bump. And just like the other rule for making things more symmetric applied to unimodal data, this is applying best to monotonic curves, okay? So the monotonic curves are either going down, you know, in one of these quadrants they're either going down like this, or they're going up. So it's monotonically increasing or monotonically decreasing. And then the decrease, it's either curved this way or it's curved that way. The increase, it's either curved this way or it's curved that way. And so now the mnemonic is, if you think about which one of these four pieces corresponds to what you're viewing in the scatter plot, think about where is this bulge, where is this bump pointing. This bump is pointing in that direction. That direction is down on the x-axis, up on the y-axis. Correspondingly, you should probably move down power transfer. This one's in this direction. That's going up on the x-axis. So your power transformations should move up the ladder on x or y, or both. Okay. Here it's pointing down on y, up on x. So that you should move down the power transformation down on the y ladder, on the vertical ladder, and up on the x ladder. And this is down on both of them. Okay? Questions? Very simple mnemonic. So you don't have to think hard about, oh yeah, what does logarithm do? How is that going to work? How is that going to fix a scatter plot? Simple rule, you see some kind of monotonic relationship with some curvature. Think about where is that curvature pointing, and that suggests the power transformations for one or other of the axes or both that should result in a straighter relationship. Okay? So, in case you didn't believe me, let's go back and see whether that works here. So I move these down here. I've got curvature in this direction. It's pointing down on the y-axis, up on the x-axis. So here's the x. I can move the x up or the y down. So let's move the y down. That's certainly getting straighter, taking the curvature out. We can move the x up. That's also taking it out. And if I move this up far enough, I've got curvature in the other direction. This says move up on the y-axis, it's pointing up there, or down on the x-axis. So I can move up on the y. I keep this going. That's saying move up on the x or down on the y. So let's just move up on the x. Let's move this up on the x. That's saying move up on the y. So I move these guys up. I'm still keeping kind of this straighter relationship. But those outliers are really sinking me. Okay. So it does kind of work here. I can think about straightening that relationship, and some of them, like that even is a pretty straight relationship, although it's got two skewed distributions for the margins. So that's a fairly straight relationship. It's saying it's not pointing anywhere. You don't have to do anything to make that relationship straighter. However, to make it these marginals more symmetric, right, I'm going to have to move up on both. So up to there. And down to here. It's a natural transformation, the logarithm of the brain weight versus the logarithm of the body weight. Log-log plot. Okay? So that works. Nice little mnemonic to allow you to choose a power transformation. Here are the effects. If I've just laid them out in a grid, changing from -2 to +2 for the power for x, from -2 to +2 for the power for y, assuming that it's straight along the center here when they're equal, so at log-log. You can see the effect. If it's here, it's suggesting which way to go. It's telling you to go that way from down here, and that will straighten out the plot. And you can also see the marginal behavior. And that's what the same plot looks like for the mammals data. Okay? So these power transformations are very, very handy. But they serve a particular purpose, making things more symmetric, unimodal things more symmetric, and straightening relationships. It's straightening monotonic curvilinear relationships. Okay? Here's another transformation. And this one, if I'm thinking about detecting dependence, so this is a little bit of a walk. I hope we have time to finish this. A little bit of a walk that I want to tell, is there any stochastic dependence between two variables, between x and y? Okay, so you know the rank transformation. Rank preserves the order and not much else. Okay, so to detect dependence, or independence, think about what that means. We've got lots of ways of defining independence based on the cumulative distribution function, for example. You can do it with the densities as well. And you think about the CDF. So x and y as random variables are independent if their joint distribution is the product of their marginal distribution, right? Remember that? Easier way, I think, to think about independence is that if the conditional distribution of x given y is just the same as the marginal distribution, then y wasn't providing any information. X's values are independent whatever y's value was. So if the conditional distribution looks the same as the marginal, or y given x, same thing, looks like the marginal of y. Okay? So if we were to look at plotting these things, where you think about the joint distribution as being the spread of those points in the plane, and then think about the marginal distribution being how they pile up on either axis, and the the conditional is to say, well, pick one value and think of what's the distribution of those points along that slice. So a slice of x, let's say. So here's an example. This is empty cars data, and what I have are the miles per gallon usage of fuel in these cars from, these are somewhere in the 1970s, I think, and these are American gallons, not Canadian gallons. So imagine that as the car gets heavier, you don't get as far on a single unit of fuel. So does this look like it's decreasing? So do these variables look like they're independent or dependent? Well, they look kind of dependent. And you can see that if I take any one of these slices, the slice of weight here, the distribution of miles per gallon is located here in this range from here to here. Whereas if I look over here, condition on a smaller weight, the location is in a different one. So its distribution is different. The conditional distribution of miles per gallon is different depending on the value of weight that you're using. So that's definitely a dependence. Is there a dependence here? Well, similar thing, that the location is certainly changing over time. Not over time, as x changes, the conditional distribution is changing. Fairly easy to detect. That's even easier because you can see that it's much more spread out here, and because we can actually see the details of the data, that these transformations are, their transformation, when I'm applying them marginally like that, they're kind of preserving the dependent structure. Okay? So that's a little bit easy. That's taking the square root of each of those. And that's the log of each, and that's darn easy to see that there's a relationship there between these two variables. So here's a different transformation, and this transformation is going to allow you to detect dependence very easily. It's going to make it difficult. It's not going to necessarily make it easy to describe that dependence, but it'll easy to tell whether there's dependence or not dependence. And that is this transformation. You know that if I have any x value here, and if I knew f of x, I could apply the distribution function to that value and get a new value u. Similarly, I could do that for y. U and v, these two transformed variables, will be uniformly distributed. We've used that a few times already to generate data. So what happens when I do that to the data with an empirical distribution function? Well, it's saying get your x and figure out what proportion of the data are less than or equal to that value. So find out what proportion is less than or equal to that value. That's the empirical distribution. I could do that for the x and for the y. That's pretty much the same as the rank, right? What's the rank of this point in the data set? The rank's telling me how many points are less than or equal to that value. So I could just take the ranks of the data and plot these pairs. Now those pairs should be uniform. Marginally they will be uniform. So I've taken out the marginal behavior of the data. But together, if they're independent, then the joint distribution should be the product of those. The product of two uniforms is just going to be uniform in a square, right? So if these things are independent, when I plot that, they should just look like uniform scatter in a square. If they don't look like uniform scatter in a square, there's some dependence. And I've removed all of that craziness about what is the marginal, what is of either one. Okay? So for example, if I'm looking at here trying to decide on dependence or not in any of these things, these are three different transformations of the mammals data, the body weight, brain weight. And here are the ranks. The ranks of that, ranks of that, ranks, because the ranks are preserved, right? These were order preserving transformations. I'm going to get the same ranks. This is dead easy to tell that that does not look like it's uniform around in this whole rectangle. There is a relationship. So going to ranks immediately, it's just becomes very obvious. In fact, if I looked at, there's a measure of correlation there that measures whether there's a monotonic relationship in the original data. That is just a correlation of the ranks, sometimes called Spearman's row. So let's look at a more complicated data set. Here's the diamonds. It happens to be got lots of measurements, the depth of the diamond, the carat or weight, the measure of the percentage of width of the top of the diamond, and the price in US dollars. And so I've got a bunch of different variables here. So this is price versus carat. There's about 50,000 observations here now. And you're thinking, does that look like there's a relationship? I'm looking for dependencies. Yeah, I think so. Gee, I don't know, I guess. Because don't forget, I could see all this just because the marginal distribution of the x's piles them up here. The question is that conditional distribution of y given x changing as x changes. Again, I don't know. It gets a little harder here. Well, those lines that I see, that could be just related to the marginal distribution of the y's. Again, a little harder to tell, but I think there's some dependence. That one, I think there's a little bit, because I see that cloud going from the top left to the bottom right. However, if I switch to ranks, all I have to do is look at the ranks of these things. Doesn't look like a uniform. And to give you some sense of what does that look like, here are some uniforms. So that's 6 samples of size n randomly selected from a uniform. So it should look like that with that many points. It should just look like it's covering this thing a uniform distribution. For the diamonds, there are the ranks. That definitely does not look like a uniform, no question. There was pretty much no question here as well, but no question there that that's got a dependency. This one does not look nearly as dependent. There may be some concentrations and some places where it's thinner, but that looks pretty uniform. So maybe there's no real dependent structure left there, or not a huge dependent structure. This one, well, now I'm starting to think, see a little bit of patterns here. Uniform than I saw in the previous one, although that still looked a little bit dense there, maybe on this tail. In that one, I could certainly see that there's non-uniformity there, that there's some dependence going on in the ranks. This one again, some dependency, not nearly that as strong as we saw in the very first plot, but there's still some there. That one, you can definitely see it. You see the piling up here, the thinning down there, piling up there. So that's not a uniform, that dependence is there. So moving to ranks gets rid of the marginal, and you can say, if I want to see, is there a dependence between a couple of variables, I'm going to move, do that transformation to the ranks. Okay? So we're out of time, but I think that's the end of the lecture.